Hello students, welcome to EPG Pathshala. I am Professor Panchapakeshan from the University of Delhi. Today we are going to discuss about the module Spontaneous Breaking of Symmetry from the paper on radiation theory in the course Physics. After studying this module, you will be able to understand what is a reflection invariance. You will see how the values of the parameters appearing in the Lagrangian help the ground state or the vacuum state to break the symmetry present in the Lagrangian. You will learn about the idea of a degenerate vacuum when two or three different types of vacuums can have the same energy. You will also learn about the spontaneous symmetry breaking phenomena. You will see that the symmetry obeyed by the Lagrangian is not due to any external agency or an external term introduced in the Lagrangian, but rather the value of the parameters in the Lagrangian or the potential can be chosen in such a way that the symmetry is not obeyed by the ground state or vacuum, which occurs at the minimum of the potential. You will learn how some fields acquire a mass while some fields remain massless. You will learn also what is the Nambu-Goldstone theorem, named after the famous scientists Nambu and Goldstone. You will learn that the presence of long-range gauge fields leads to the disappearance of the massless boson, and they acquire a mass by the gauge bosons, which were massless at the beginning. We have seen that various symmetries are present in a Lagrangian of a system. The various energy states of the system obtained by solving the equation of motion, or often by looking at the potential energy V of the system, usually obey these symmetries. The symmetries also simplify the mathematical procedures of getting the solutions. In 1957, Bardeen, Cooper and Schrieffer, normally abbreviated as BCS, gave a very successful theory of superconductivity in condensed matter physics. It was realized soon that the ground state of the system did not obey the symmetry of the original Lagrangian. There was loss of gauge invariance, which the original Lagrangian obeyed, but the ground state did not obey. Generally, many times, by suitable changes in the parameters of the Lagrangian, we can ensure that the ground state, which is the vacuum state from which excitations to higher energy states arise, this vacuum state does not obey the symmetry obeyed by the Lagrangian. This is called spontaneous breaking of symmetry. This phenomena has enabled the renormalization of weak interactions. Quantum field theories generally suffer from the appearance of infinities while calculating physical quantities like cross sections for scattering or binding energies. A consistent way to handle them and obtain finite results is called renormalization theory. Electroweak theory of Salam and Weinberg, developed in the 1970s, was shown to give a renormalizable theory by 't Hooft a few years later. It unites electromagnetic and weak interactions into what is now called electroweak theory. The idea of spontaneous symmetry breaking and the appearance of massive gauge bosons is an essential part of the theory. In section 3, we discuss the idea of symmetry breaking for a scalar field obeying reflection symmetry, that is phi going to minus phi. We see that for certain values of the parameter, we get spontaneous symmetry breaking. In section 4, we extend the discussion to complex scalar fields. We then see how the symmetry is restored in a different way by the combination of the ground state and the zero mass excitations. These massless excitations for particles are called Goldstone bosons. In section 5, we extend these ideas to complex scalar field interacting with a gauge field. We then see that the gauge bosons acquire mass by combining with component of the scalar field. This process, now called Higgs phenomena, is discussed in section 6. In section 7, we look at another example from condensed matter physics, which illustrates these ideas given above. This example is the phase transition to a ferromagnetic ground state below the Curie temperature for a magnetic system. The ground state in this system is magnetized with all the spins of the magnetic domains aligned in some specific direction. This breaks the spherical or planar symmetry present above the Curie temperature. Spin excitations or spin bosons play the role of Goldstone bosons and cause a slow rotation of the direction of magnetization. As the forces involved are short-ranged, the energy required to do this approaches zero in the wavelength when the wavelength of spin boson becomes large. Thus, the spin excitations or bosons restore the spherical symmetry. When long-range forces due to gauge fields are present, the energy required to rotate the ground state is finite. Then the gauge bosons acquire mass and the massless Goldstone bosons disappear. We first consider the spontaneous symmetry breaking of a scalar field. We start with the simplest case of a single component or real scalar field, which is usually called the phi-4 field. Consider self-interacting scalar field phi with phi-4 interaction given by the Lagrangian. Lagrangian is equal to half d mu phi minus half mu squared phi squared minus lambda by 4 phi to the power 4. d nu dl d nu phi is equal to d nu phi and dl d phi is equal to minus mu squared phi minus lambda phi cubed. So the Lagrange equation of motion is d nu of phi plus mu squared of phi is equal to minus lambda phi cubed. Writing the Lagrangian as T minus V, that is the kinetic energy T minus the potential energy V, equation 3.1 gives potential is equal to half mu squared phi squared plus lambda by 4 phi 4. The stationary points of the potential V are given by the solutions of the equation dV d phi is equal to 0, which is equal to mu squared phi plus lambda phi cubed, or phi is equal to mu squared plus lambda phi squared is equal to 0. We first consider the case mu squared greater than 0. Then minus mu squared by lambda square root is imaginary. And the solutions are phi equal to 0 or phi equal to minus mu squared by lambda. The ground state or vacuum has phi equal to 0 and has the reflection invariance R going from phi to minus phi that the Lagrangian had in the beginning in the shown in the figure 1. We now consider mu squared less than 0. Phi is equal to then minus mu squared by lambda, and for these phi we have the lower and stable states. We define V, the vacuum expectation value of phi, as ket 0 phi bra 0 phi ket, and this is equal to square root of minus mu squared by lambda. Now R symmetry is broken as the point phi equal to V and minus V are different in energy. If we define phi prime equal to phi minus V, we get back the vacuum expectation value of phi prime as 0. And the potential then becomes half mu squared phi prime squared plus mu squared v squared plus twice phi prime v mu squared plus lambda by 4 into the set of terms given there, which is equal to half of mu squared phi prime squared mu squared v squared plus twice phi prime v mu squared plus lambda by 4 into phi prime 4 plus 4 phi prime cubed v plus 6 phi prime squared into minus mu squared by lambda plus 4 phi prime v into minus mu squared by lambda plus v4. The coefficient of phi prime term vanishes and phi prime squared term has coefficient mu squared. So mass of phi prime field is square root 2 times the mu magnitude. Complex scalar field in the abelian group U1. When phi field is complex, we take phi equal to phi 1 plus I phi 2 divided by square root of 2. Phi 1 and phi 2 are then real. The Lagrangian is d mu phi star d mu phi minus mu squared phi star phi minus lambda phi star phi, the whole thing squared. And under the transformation phi going to phi into exponential I lambda in the Lagrangian, we have invariance. This kind of phase change belongs to what is called U1 symmetry. In terms of phi 1 and phi 2, we can write the Lagrangian as d mu phi 1 d mu phi 1 d mu phi 2 d mu phi 2 minus mu squared by 2 phi 1 squared plus phi 2 squared minus lambda by 4 into phi 1 squared plus phi 2 squared, the whole thing squared. For mu squared greater than 0, it is a complex scalar field of mass mu. For mu squared less than 0, V phi has the form half mu squared into phi 1 squared plus phi 2 squared plus lambda by 4 into phi 1 plus phi 2 squared whole squared. The two terms in equation 4.3 have opposite sign and V has a minimum at phi 1 squared plus phi 2 squared is equal to twice phi mod squared, which is equal to minus mu squared by lambda. So minimum occurs along a circle of radius minus mu squared by lambda, which by definition we call V. See figure 3 below. Let the vacuum expectation value of phi 1 be equal to V and that of phi 2 be 0, so that the shift of the minimum or ground state is along x1 axis. We take phi 1 prime is equal to phi 1 minus the vacuum expectation value of phi, or phi 1 prime is equal to or phi 1 is equal to phi 1 prime plus V. And so d mu phi 1 prime is equal to d mu phi 1, as V is a constant. Taking Lagrangian as half d mu phi 1 prime d mu phi 1 prime into d mu phi 2 into d mu phi 2 minus V, we have for the potential energy V this expression which is given below, which is finally equal to V equals minus mu 4 by 4 lambda plus lambda V squared into phi 1 prime squared into lambda phi 1 prime into phi 1 prime squared plus phi 2 prime squared plus lambda by 4 phi 1 prime squared plus phi 2 squared whole squared. There is no term with only phi 2 squared, so phi 2 is massless. The phi 1 squared term has coefficient lambda V squared, which is by definition half m squared, so m is then given by square root of 2 lambda V. M is equal to square root of 2 into the magnitude of mu. So phi 1 prime field has mass square root 2 mu, while field phi 2 is massless. This is an example of Nambu-Goldstone theorem, which states that massless bosons, now called Nambu-Goldstone bosons, appear if a continuous symmetry is broken. The number of Nambu-Goldstone bosons is equal to the number of broken generators of the symmetry group. In our case, invariance under phase change, phi going to phi into exponential I lambda, called the U1 group, has one parameter, lambda. And this is broken, so we have only one massless particle. Spontaneous breaking of symmetry. To understand the role of Goldstone bosons, one may look at the lowest or ground state of the complex scalar field. Any point on the circle of radius V can be the ground state. We can choose values of the vacuum expectation value of phi equal to V by giving suitable values to phi 1 and phi 2. All these ground states have the same energy and are said to be degenerate. The phi 2 Goldstone boson enables the passage from one degenerate state to the other degenerate state. The circular symmetry for values of phi 2 along the circle in this way restores the original U1 symmetry. So, a symmetric Lagrangian can have a symmetric ground state or a ground state of broken symmetry which is combined with a Goldstone boson to access all the other degenerate vacuum or degenerate states. This was first realized by P.W. Anderson in connection with superconductive ground state. In this sense, the symmetry in phi 1, phi 2 space is restored even with a broken or non-symmetric ground state. This is often called spontaneous breaking of symmetry, as there is no explicit symmetry breaking interaction term in the Lagrangian. Gauge fields and gauge symmetry. If we demand invariance under the local transformation, phi going to exponential I lambda as a function of x into phi, we have to introduce, as we saw for the electromagnetic field, a new field through a covariant derivative which brings in the new field. This field is usually called the gauge field. Electromagnetic field is a well-known example. The normal derivative d mu is replaced by the covariant derivative capital D mu, which is equal to d mu plus I e a mu. A mu is the new field called gauge field. The Lagrangian equation 4.1 then becomes Lagrangian is equal to d mu plus I e a mu into phi into d mu minus I e a mu into phi star minus mu squared phi star phi minus lambda phi star phi whole squared minus 1 over 4 f mu nu, which is the Lagrangian part for the electromagnetic field. Proceeding as in section 4 for mu squared greater than 0, V has a minimum at phi equal to 0. When mu squared is less than 0, in general, twice phi prime squared is equal to phi 1 squared plus phi 2 squared, which is equal to minus mu squared by lambda, which is equal to V squared. And phi prime can be written as V over root 2 plus phi 1 prime plus phi 2 over square root of 2. If we take the vacuum excitation value of phi 1 equal to V, as we did in the last section, then phi 1 prime is equal to phi 1 minus V with a real V. In this case, only field phi 1 is shifted and it acquires a mass square root 2 mu like in earlier case. In addition, the covariant term d mu gives E squared a mu V squared by 2 minus IE a mu V by root 2 d mu phi 1 prime root 2 plus IE a mu V by root 2 d nu phi root 2 plus IE a mu V by root 2 d mu minus 1 phi 2 by root 2 minus IE a mu V by 2 d mu root 2 plus IE mu phi 1 prime by root 2 d mu phi 1 prime by root 2 and similar terms involving three fields. And this is equal to half E squared V squared into a mu plus EV into a mu d mu phi 2 plus terms with three fields, as second term cancels the third term in the earlier expression. Thus, the E squared V squared a mu term indicates that the photon has acquired a mass E times V. Phi 2 field is still massless, but the a mu d mu phi 2 is an odd mixed term indicating that a propagating photon could turn into a phi 2 field, so phi 2 field does not seem to be a very physical field. In fact, phi 2 field can be eliminated by a gauge transformation, as we see below. Infinitesimal gauge transformation. We have phi 1 prime is equal to phi 1 minus V, or phi prime is equal to phi minus V by root 2. For infinitesimal lambda, phi prime is equal to goes to phi double prime, which is equal to 1 plus I lambda into phi prime. So square root 2 of phi double prime is equal to phi 1 prime plus I phi 2 prime plus I phi 1 prime lambda minus phi 2 prime lambda. So phi 1 double prime is equal to phi 1 prime minus phi 2 prime lambda, and phi 2 double prime is equal to phi 2 prime plus phi 1 prime lambda, and this is equal to phi 2 plus phi 1 lambda plus v times lambda. So phi 2 not only undergoes a rotation but also a translation in the phi 1, phi 2 plane. We can choose lambda to make phi 2 equal to 0. Thus phi 2 disappears. Thus we have left with one field, phi 1 of spin 0, and another field a mu of spin 1. Both are massive. While phi 1 has 1 degree of freedom, the massive a mu has 3 degrees of freedom, giving us a total of 4 degrees of freedom. This replaces the 2 degrees of freedom of original phi and the 2 degrees of freedom of the massless a mu. Higgs phenomena. This phenomena of the gauge field acquiring a mass is called the Higgs phenomena. It was given by Higgs and a few others in 1974. After the Higgs particle in weak interaction was discovered in 2012. Higgs and Engelbert got the Nobel Prize for this discovery in 2014. In electroweak theory of Salam and Weinberg, there are 4 zero-mass bosons. 3 of them become massive and mediate the weak interaction, while the remaining one is massless photon, which mediates the electromagnetic interaction. However, it was not known if the theory could be made free of mathematical infinities and made renormalizable when gauge fields acquire mass. Only after Atoft and Weltman showed that the theory with massive bosons was renormalizable that the theory became acceptable. Ferromagnetism and spin bosons. In ferromagnet, there are small magnetized domains. These point in random directions due to thermal motion when temperature is greater than the Curie temperature. Below the Curie temperature, there is a phase transition and all spins are aligned in one direction. This, however, means spherical or planar symmetry is broken. There is the Goldstone boson which changes the common direction of alignment. This is called a spin wave, which are of long wavelengths. It causes small variation of the direction of magnetization. As the ferromagnetic forces are of short range, it requires very little energy to change the directions. However, when there are long-range forces due to gauge fields with massless bosons like the Coulomb field, then it requires a finite amount of energy. The excitations are massive, and so the gauge bosons also acquire mass, as we saw in section 5. The massless Goldstone bosons disappear as they have been absorbed by the massive gauge bosons. So we see that ferromagnetism is an example of what we have discussed or similar to what we have discussed earlier. In this module, we have learnt about what is reflection invariance. You have also learnt how the values of the parameter appearing in the Lagrangian help the ground state or the vacuum state to break the symmetry present in the Lagrangian. You will have also learnt about the idea of degenerate vacuum. You also learnt about the spontaneous symmetry breaking phenomena. You have seen that the symmetry obeyed by the Lagrangian is not due to the external agency, but rather the value of the parameters in the Lagrangian or the potential term. It could be a parameter in the Lagrangian, or we could isolate the potential term and consider it separately also. This can be chosen in such a way that the symmetry is not obeyed by the ground state or the vacuum state, which occurs at the minimum of the potential. You will have also learnt how some fields acquire a mass while some fields are massless. You have also learnt what is a Nambu-Goldstone theorem, which predicts the presence of massless particles. You will also have learnt that the presence of long-range gauge fields leads to the disappearance of the massless boson and the acquiring of mass by the gauge bosons, which were massless at the beginning.